Hello, ng-conf. I'm Alex Rickabaugh from the Angular Framework team. I'm excited to be here at this virtual ng-conf alongside my good friend and colleague, Joost Koehoorn, to share some of the work we've been doing lately with the Angular compiler. And I want to start by showing a short little demo. We've been working hard on updating the Angular language service for Ivy, and I wanted to show you one of its new little features. So I'm here in Visual Studio, and I have just a very basic application that I've built. It only has one component called the app greeting, and app greeting displays a greeting. So here we have an h1 element, and we're echoing out this greeting.message. So you'll notice that language service is actually working here, so we can see the types of various things in our template. It's pretty cool. But what I wanted to show you is something a little more interesting. So greeting here is this field that we initialize, and it has an interface type greeting that requires it to have a message. And if we ask TypeScript to show us all of the references to this message field, we'll get the results we expect. Its interface declaration. We'll see that it's used once during initialization here. But also we get some results from the template. We can see that message is in fact used in this template expression. And that's pretty cool. The language service couldn't do this before. Cool, right? Mostly we've been focused on supporting all of the existing language service features, but this one was so highly requested and so cool that we just couldn't resist adding it. And it was actually fairly easy to get working because our new language service is using the Angular compiler under the hood. Our compiler doesn't just power find references, it actually is behind a lot of the interesting work that's happening in Angular today. So it might be interesting to explore how our compiler understands Angular code and some of the things we've been able to do with that understanding. The term compiler is often used vaguely, especially in the context of Angular. So I want to clarify, first of all, what I mean when I say the compiler. This is especially true since most Angular users these days interact with our compiler only indirectly through the CLI. And that would be through the ng-serve and ng-build CLI commands. These commands configure and run a Webpack build that pulls in a bunch of different tools and operations. And one of the tools in this stack is the Angular compiler proper, which we call ngc. And this is the tool responsible for turning your Angular applications that are written in TypeScript into the JavaScript that can actually run in web browsers. ngc is itself a wrapper. It's built on the TypeScript compiler APIs that Microsoft provides. You can compile Angular code with the plain TypeScript compiler if you want, and that's exactly what happens if you're using Angular's JIT mode. ngc performs the exact same functions as the TypeScript compiler. It translates TypeScript code into JavaScript. But ngc also understands Angular decorators. It'll recognize components and directives and ng modules, all of the building blocks of Angular applications, and it can translate them into their runtime forms in advance. Most importantly, it takes the HTML templates of components and generates the JavaScript to render them using Ivy runtime instructions. Angular's compiler faces some challenges in accomplishing these goals that the regular TypeScript compiler does not. To understand why, let's look at what's required for TypeScript to compile a file versus what Angular needs to do. In TypeScript, each TS file is processed by the compiler, and that results in a JavaScript file as output. And this is one-to-one. Every JavaScript file, the contents of that file only depends on the particular TypeScript input file. And that's a really nice model for a compiler because it's very straightforward and easy to implement. Of course, type checking is another story, but we can ignore that for now. One input file to one output file. Very straightforward. Angular, on the other hand, doesn't follow such a clean model of compilation. Our compiler can't just look at a single TS file and know what the output JavaScript should be. And that's because the Angular decorated classes don't live in isolation. The most obvious example of this is a component. Components have templates. And if that template lives in an external HTML file, our compiler needs to understand that dependency. And it has to read the template file in order to produce JavaScript for the component. And it doesn't stop there, right? Components can use other components in their templates, or directives, or pipes. Which ones? Well, that depends on what your ng modules say. So in order to fully compile a template, our compiler has to not only understand the HTML, but also what the ng modules are saying about the application structure to know which directives and pipes can be used in that template. And Angular has one more trick up its sleeve here. When you write something like a component decorator, you can actually use expressions inside of it instead of literal values, just like you can at runtime. Our compiler is able to follow these in some cases, but that means your component might depend on the contents of not just the file it's written in, but some of the files that it imports as well. Our compiler solves this problem by performing a few steps on top of the default TypeScript process. In particular, we add 3 extra phases of compilation, which we call analyze, resolve, and compile. So I'm going to quickly walk you through each of them. In the analyze phase, we're looking at every class in the program, one at a time, and particularly we're looking for the ones with Angular decorators. And we're trying to understand what that decorator is telling us. If it's a component, for example, we're looking for references to template files or style sheets, and we're loading those as needed. And if you wrote any fancy expressions in the decorator, we're evaluating those and trying to follow the imports in order to get the data for that particular decorator. But at this point, we're looking at each class for the first time in isolation. So when we're looking at a component, we might not have seen its module yet. So we don't know what that module is or what other components or directives might be used in that template. That happens during the resolve phase. After we've learned everything we can from each class in isolation, we begin to consider the entire program. And this is where we combine the information in each ng module to give a complete picture of the application structure, which directives and pipes are used in all of the templates. There's a few other kind of global processes that we need to do as well at this time. But in general, we try to keep this step as small as possible because it has to happen on every compilation, no matter what you change in between ng-serve runs. So finally, when we've understood all of the classes individually, as well as the whole application structure, and when TypeScript has finished type checking the application, we're finally ready to generate code. And we ask TypeScript to do this to produce JavaScript for each TypeScript file input. And as part of this process, we perform a compilation step for every class that's decorated. This step takes everything we've learned about that class, whether it's a component or directive, and how it relates to the rest of the program, and generates any Angular JavaScript code that might be needed for that class at runtime. For components, right, that's the compiled template. And this code gets added to the class before TypeScript converts it to JavaScript and writes it out as output. A really interesting feature of this architecture is that the steps which understand Angular code and the steps which actually generate the output JavaScript are distinct. And that allows us to do some really interesting things. I'm going to turn this over to Joost, who's going to walk you through one of them, the Angular linker.
Hi ng-conf. My name is Joost Koehoorn from the Angular framework team, where I have worked on the Angular compiler for the past few years. Now that Alex has given an overview of the compiler and its various phases, let's expand on that insight by taking a look at Angular libraries. Many of you have likely seen these messages being printed when running ng-build. It's been this way since the introduction of Angular Ivy in version 9. It is the Angular Compatibility Compiler, or ngcc in short, which is converting existing Angular libraries to become compatible with the Ivy rendering engine. This has allowed us to continue to support libraries that have been published years ago for older versions of Angular during the transition from Angular's previous rendering engine Vue engine to Ivy. Unfortunately, ngcc has quite a hard job to do. Existing libraries have been built using a format that was specifically designed for the Vue engine compiler. If you look inside a library, you'll find that it contains the bundled JavaScript files just like any other npm package, together with a special metadata JSON file that only the old Vue engine compiler is able to understand. Since Ivy, the metadata JSON file is no longer used. Instead, the compiler consumes libraries by extracting the necessary information from TypeScript's declaration files. So, in order to allow the Ivy compiler to use a library, it needs the library's declaration files to be updated. Also, the library's JavaScript code needs to be updated to contain the compiled Ivy code. This has been the job of ngcc, which has allowed mostly seamless consumption of libraries while not breaking the ecosystem of existing libraries. If you take a look under the hood of ngcc, you'll find that it has to execute all three phases of compilation as Alex has explained. All of this work makes ngcc relatively slow to run. Even more so, the resolve phase makes the result of ngcc dependent on other libraries, which means that caching of ngcc's output is restricted to all of the modules or nothing. As mentioned before, ngcc has been designed as an intermediate tool to help during the transition from Vue Engine to Ivy. Going forward, however, a new way of publishing libraries is needed as Vue Engine is going away. One of the IDEs for its replacement has been to just publish Ivy compiled libraries to npm. In the end, however, we decided not to choose this option as it wouldn't allow us to provide the stability of Angular libraries as you've known it for the past few years. Instead, we've opted for a new compilation mode that we call partial compilation. What we've learned from ngcc is that the analysis and resolve phases can be done at the time a library is built, exactly the same as it would for applications. Only the compilation phase is changed, such that the compiler no longer generates fully compiled Ivy definitions, but rather what we refer to as partial declarations. Let's see what that means using an example. Here you see a small component. Notice how it imports its selector from another file. The compiler has to statically evaluate this import to determine the selector string for this component, which is done during the analysis phase. Then, notice also how it uses the ng-for directive and a component from the library. These declarations can be used in the template of order component because somewhere in the library there exists an ng module that has these declarations in scope. This overarching knowledge across decorators is pieced together during the resolve phase. Now, let's have a look at the partial declaration of this component. You can recognize them by their ng-declare prefix. Each Angular decorator is compiled into one or more of such function calls. Notice that the selector is no longer hidden behind an import. The compiler has completed the analysis phase and its results has been stored in the partial declaration. Also notice that the partial declaration contains the version of the Angular compiler that was used to compile the library, together with the strange ng-import property. These details are needed when the partial declaration is compiled into its full definition, but more on that later. If we look further into the partial declaration, we'll find that it also lists the components, directives and pipes that are used in the template. The library's order item component is present along with its public component metadata because it was used in the template. And also the ng-for directive from Angular Common is present. This shows how the results of the resolve phase have also been incorporated into the partial declaration. To summarize, partial compilation mode converts the Angular decorators into partial declarations, where all necessary information has been resolved and gathered together. This is powerful, as it allows the partial declaration to be fully compiled independently when the library is eventually used in an application. That brings us to the Angular linker. A partially compiled library has to be converted into fully compiled code according to the version of Angular that is used in an application. This task is done by the Angular linker, which is implemented as a Babel transform to process individual source files. Because source files are processed independently from each other, the generated output can be easily cached. To get a better feel of how this works, let's have another look at the example we looked at before. The Babel transform inspects all function calls in the source file to detect the ones that correspond with ng-declare functions. Their argument is then fed into the Angular compiler to finish the AOT compilation. In this case, the ng-declare component call is being replaced with define component, and its argument describes the fully AOT compiled component definition. Notice how the ng-import expression that was present in the partial declaration has been used to reference the Ivy instructions. The version information is no longer present, as it is not needed in the AOT compiled definition. So, how to start using the Angular linker, you may wonder. First, a library needs to be compiled and published using the partial compilation mode that is being released in Angular 12. We're not yet making it the default option for library distribution just yet, but if you are a library author and intend to only support Angular 12 with UP, you can start publishing your library using partial compilation mode to provide your users with the benefits of the Angular linker. During application builds, the Angular CLI will automatically detect partial declarations and run the Angular linker transparently behind the scenes. As an application developer, this means that you don't have to do anything special to start leveraging the new way of library distribution. As a fallback strategy, partial declarations that have not been pre-compiled using the Angular linker will be executed at runtime to initiate the linking step using the JIT compiler. So, in conclusion then, the partial compilation mode, together with the Angular linker, continues to offer our users with the stability and compatibility of libraries as before, while enabling faster builds and easier caching of compiled libraries. Library authors benefit from the same AOT compilation experience as application builds. All of this while allowing Angular to retroactively fix bugs and to evolve the rendering engine as needed for a bright Angular future. That's it from me. I'll hand it back over to Alex to talk about the Angular language service.
Hello again. Now that we've seen how the compiler is being leveraged to improve the story around building libraries, I wanted to show you how we're also using it to improve the developer experience in your IDE. And to do that, let's go back to the find references example that I showed earlier. It was possible for us to build that feature because with Ivy, the compiler is now powering our language service. And this hasn't always been the case. The previous language service, the one that was implemented using for view engine applications, was mostly independent. It interpreted Angular code on its own. So how do we do this? And most importantly, why did we do this? So remember those three phases from earlier? Analyze, resolve, compile? We actually have a fourth one called type check. And in particular, this is an operation that we call template type checking. And this phase is the source of any errors that you might see if you try to build with an error in your template. Something like an incorrect type, or an invalid binding, a component that doesn't exist, etc. Producing these errors is the most challenging job that the compiler has. And it's hard for a pretty straightforward reason. Templates are written in HTML, and TypeScript, and especially its type checker, don't understand HTML. So if we want to use TypeScript to check what's going on in the templates, we have to find a way of converting them into TypeScript code that it can understand. And that's what our template type checking engine does. So here we have a greeting component, and it has a very simple template. It's just going to display greeting.message as a text binding. And whatever type this greeting object is, it needs to have a message property, or that's not going to work. Also, the component probably should have a greeting property as well. So under the hood, we convert this template into a structure that we call a type check block. And this is TypeScript code that doesn't get compiled or executed, right? You as a user will never see it. It only exists for us to feed to the TypeScript type checker and get back any errors that it might contain. We can then show you those errors as actual template errors. So in this type check block, we've expressed the text binding as a bare expression. It reads the greeting field off of the component called CTX. And if the component does not have a greeting field, TypeScript's going to complain about this. It then reads the message property off of context.greeting. And again, if message doesn't exist, TypeScript is going to yell about that too. So let's make this example a little more complicated. Suppose we use ng-if to check if the greeting is null or undefined or something like that before we read the message. The type check block that's needed to validate this template a little more is a bit more complicated. First, we're going to use a little type trick to figure out the type of ng-if. That'll allow us to type check that the binding that we're passing to it actually satisfies its input type. Right? We can assign the greeting field of the component to the ng-if's input for its condition. And because ng-if only cares about truthiness, that check will almost always pass. But ng-if also declares to the compiler that it behaves as a conditional. So our type check block contains an if block here that has the ng-if condition repeated. And that will allow TypeScript to narrow the type of context.greeting to truthy inside the block, just like you'd expect with a TypeScript level if statement. So that allows us to properly type check an ng-if. Back when these type check blocks were first designed, Angular actually didn't have a language service. But as it turns out, they are incredibly useful for implementing language service features, including really tricky and advanced ones like find references. To understand why that is, it's useful to know how find references works in pure TypeScript, in the TypeScript language service itself. So TypeScript has a find references operation that you can do. And given a file name and a cursor position within that file, somewhere you're pointing your mouse, TypeScript can tell you all of the places where the symbol under that cursor appear, right? And that's very useful. So in our greeting component, if we use TypeScript's find references on the message field, it can tell us the other places in this component where message is referenced. And that's where we get really tricky. Just like our compiler is based on the TypeScript compiler, our language service is also based on TypeScript's language service. But because our compiler knows how to create TypeScript code that represents templates, we can also feed that code to TypeScript's language service and get back results for templates as well as for the application. So if we ask TypeScript to find references to the message field in our component, it'll not only find us the answers in the application code that you wrote, but it'll give us answers for those type check blocks as well, and we can convert them back and show you those results in the context of your template. And that's the end of our little tour through the compiler. We've learned about its architecture and how it functions as an engine for understanding Angular code. We've seen how this design is allowing us to make building with libraries faster without affecting the stability of our ecosystem. Right? And we've seen how it enables advanced features in the language service. By the way, if you haven't already, please try out the new Ivy language service. It's an opt-in preview in version 11.2. You can turn it on in the extension settings page, and it'll be the default experience starting in Angular 12. We're really looking forward to seeing what new kinds of tools and experiences we'll be able to build and see where this design takes us. Thank you very much.